Well, good morning. It's 11:32 on the 12th of November, 2020. It's supposed to be linear algebra class. Right now, I'm the only one here. Hopefully, others will be coming in. It's a couple minutes late getting started because I wanted to go back and check and make sure that the Blackboard had posted correctly the Zoom meeting announcement. It was there correctly, so I assumed all of you were able to see it if you checked it, but right now I'm the only one here. Um, I have a fairly major announcement I want to make. One more that's a little, is still important, but not as maybe crucial to the school as the others. But it would be good for you to hear both of those. So I think I'll wait till at least one student is in the class before I make the announcement. Now, if it gets to be the end of the class, which I hope this won't be the case, and no one's shown up yet, then I will go on and make the announcements then. So what I'll do now is get started where we left off last time. We're in chapter 4, which is vector spaces. And now I can't remember now. I've got to check on this because I was running out of time last time, and with Veterans Day, and I was just exhausted and didn't do a lot yesterday. I didn't print a lot of things, but I didn't do that much active stuff. I've got to check and make sure I posted your third test. If I haven't, I'll try to get that done today or tomorrow. So we're in chapter 4, and like I said before, chapter 4, the title is vector spaces, and finally somebody's here. I think it's Kira. So let me get Kira marked here. That's good to see. That means that Blackboard did post correctly. All right, so Kira is here. All right. Hopefully the two Y chromosomes will be showing up sometime. So Kira, welcome. Right now it's only showing one person at a time. I don't know why. Sometimes it does this and sometimes it doesn't. Most of the time I see 4 or 5 at a time on the side. Now I only see one. So if the others pop in, I won't be able to see them because I only see one at a time. So if you have any sense that anyone else is trying to get in the room, let me know. Any questions, issues, concerns? We're already recording. Anything before we get going today? Okay. Now here's a couple of issues, and this is really not very important for this class, okay? But you know, interact with other people who are not graduating, because all 3 of you are graduating this term. But there is a huge push, big push for students to get registered next week. So what they're going to do is have all faculty member who can come, I can't, back on campus next week to help with advising and helping students get registered for spring term. Evidently the counts are way, way, way down. When I'm talking about counts in this context, I'm saying students enrolled in spring term way down, so they're going a big push to get students registered next week. I know you won't be involved in that, but you probably do know other students who will be here in the spring. Encourage them to do that. Now, actually, what I'm encouraging students to do is get your advising done today and tomorrow, and get registered today and tomorrow so you don't have to go to campus next week, because the counts, now I'm talking about the COVID counts, they're climbing like crazy. It's just about every day we set a new record, maybe not for the state, but for the country. In number of cases, it's really getting out of control. So I would advise you, get your advising done virtually, get your schedules done virtually, and not have to go to campus next week. So please encourage your friends, encourage people you know. I don't know, is Kaya enrolled for the spring or not? I don't know. Anyway, encourage people to get advised and registered as soon any way they can. Okay, that was one announcement. The second one, part of this may not sound like it pertains to you, but part of it does. Mr. Matthew West, who's working on his doctorate at University of Alabama, is taking a statistics course this term, and part of his statistics course is to come up with a collecting data, analyzing the data. So what he's chosen is perceptions and things to do with the COVID virus, as in which of the forms of instruction do you appreciate or like the most, the face-to-face, virtual, or online. Okay, that's one area that he's investigating. Another, do you feel like COVID has influenced your educational experience positively, negatively, whatever? Okay, so, and there's probably more to his study than that, but those are the things I got out of it. So please do that survey. He says it's 5 minutes or so. That's not much of your time. You're in 3 of my classes. I posted them in all 3 classes. So anyone that you want to go to, it's on announcements. In any one of the 3 classes you're in, go to those and do his survey. That'll help him collect data, help him hopefully do well in his statistics course. No personal information will be given out or anything like this. It's probably not even going to lead to publishing or anything else. It's just a assignment in his class, and we're trying to help him out. Okay, any questions, concerns, issues, problems? Okay, now as I was saying before, probably said a couple of times now, we're in chapter 4, vector spaces. We're in section 4.1, and this is vectors in Rn. Now, that's not registered nurse. R superscript n, that means R, it doesn't quite mean to the nth power. It's a real number system in multiple dimensions. Real number system in one dimension is your number line, okay, going from 0 negative and 0 positive. That's the real number system. That's R1. R2 would be the plane, okay, XY coordinate plane, 2 dimensions. You represent points on the number line with one number only. In the plane, you represent points by ordered pairs. R3 would then be 3 space. That's space as we know and understand it. You have a horizontal component, a component that goes perpendicular to that, say in the ground plane, and then one that goes vertically. Okay, that requires 3. That's R3, requiring 3 ordered triplets to define any point in space. Now, in linear algebra, we move into hyperspace. Okay, we deal with things we can't picture any further. We just deal with the spaces. Rn, that would be n dimensions. Even though we live in 3-dimensional space, we can talk about n-dimensional space. Okay, so the top of page 155 goes over what we've just been saying. A discussion of vectors in the plane can be extended to a discussion of vectors in n-space. And if you're in n-space, Rn, then you represent a point in that space, a vector in that space, by an ordered n-tuple. Remember, a number represents something on the number line, an ordered pair represents something in space, an ordered triplet represents something, ordered pair represents something on the plane, an ordered triplet represents something in space. An ordered n-tuple would represent a vector in n-space. I can't picture that. I really cannot, okay? But I can imagine it. I can't picture it, but I can imagine it. For example, an ordered triple in the form of x1, y1, z1, x x1, x2, x3 is an ordered that's an ordered triplet, or quadruple in whatever 4 space is would be x1, x2, x3, x4, okay, defining a value in each of those 4 dimensions, which I can't picture, okay. A general n-tuple is of the form, and if I were doing this in another course, and this author in another course, he would put an open angle bracket. They are not using them here. Those opening up parentheses, x1, x2, x3, x4, x5, all the way up to x sub n, and that would represent an n-tuple in n-space. The set of all n-tuples in n-space is represented by r superscript n. That's what we've been talking about so far, and I think we beat it to death, so hopefully it's okay. An n-tuple x1, x2, x3, x4, all the way up to x sub n can be viewed as a point in Rn with the x sub i's as the coordinates, or can be pictured as a vector in Rn with the origin being the initial point and that point that you had up there in n space, that being the terminal point in Rn. Okay, so the x sub i's would then be components of a vector or coordinates of a point. Okay, as with vectors in R2, in the plane R2 or Rn, they're equal if and only if corresponding components are equal. Same thing we had in R2, R3, Rn. In the case of n equal 2 or 3, the familiar xy or xyz notation could be used, but for higher level R4 through Rn, anything higher, we usually use the same variable just with subscripts. So the sum of 2 vectors in Rn, scalar multiples of a vector in Rn, are the standard operations in Rn and are defined like this. And because this has subscripts, I'll write them out. It's going to be ugly. So let's let you, now I'm writing this as if it's a vector, okay? And this vector is a vector n. These are the components of the vector. U sub 1. The pen is not working well today. See, it just will not write some numbers well. Dot, 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 up to and including U sub n. Those are the n components of this vector u in n space, Rn. And vector v would be correspondingly the vector who has these components, v sub 1, v sub 2, v sub 3, comma, dot, 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 up to and including v sub n. Now, both of these vectors have n components, so they're in the same space, R superscript n. These are vectors in, I'm just going to write them like this, in Rn. They're both are elements in Rn. And C is a real number. Any real number in the world, positive, negative, fraction, decimal, rational, irrational, it doesn't matter. Now, a lot of times we won't let it be 0, but it could be. There's nothing to keep it from it. Now, first, vector addition, the sum of u plus v in Rn would then be, those are vectors, this would be, of course, u sub 1, can't get the pen to write, u sub 2, u sub 3, that won't write a 3 to save itself, okay, dot, 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 and the dots run together, up to u sub n, plus v sub 1, v sub 2, v sub 3, there it wrote it better, dot, 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 v sub n, okay. What would that be? That would be u sub 1 plus v sub 1, comma, u sub 2 plus v sub 2, comma, u sub 3 plus v sub 3, comma, dot, 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 comma, u sub n plus v sub n. Just add component by component, and that gives you your new vector. And that is a vector, okay? Now, the scalar multiple, that's vector addition, scalar multiple of u by c would be c times vector u, and that would be a vector also cu1, comma, cu2, comma, cu3, comma, dot, 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 up to and including cu sub n. Okay. Those are our standard definitions for vector addition and scalar multiplication in Rn. Now, I'm going to alert you to something. You can have alternate definitions of vector addition and scalar multiplication. Okay, you can, and they'll do it. Frankly, I don't see why. I guess there are practical reasons where you'll sometimes do that, but it's mostly coming up in the future, getting you to distinguish from what is a realistic, and what the title of this chapter is vector space, as opposed to something that's not a good vector space. Okay, but this is your definition for the standard operations in Rn, and those are simply vector addition and scalar multiplication, and this is how they're defined. Now, that leads then to, as in R2 and R3 and all spaces, a definition of the, oh, and here comes Jesus. So let me get him in and marked in the roll book. I don't want to drop my pad on the floor, so hold on, we'll be here in a minute. All right, so we only need James. We get James, we got it knocked. Okay, now Jesus, I don't know if you can hear me yet, can you? See, a lot of time you can. Okay, good. I just wanted to point it out to you, a couple of announcements. The first one really doesn't apply to you or any of you in the class, because all three of you are graduating this term, okay? But if you know of other students, and I know you probably do, they are making a huge push to get students registered for spring term next week, okay? And they're having all faculty go to campus who can. I can't, but all faculty who can go to campus, they're having us go to campus, not me, but many of the others, and they're going to be manning tables in a couple of different buildings, one on Birmingham campus, one on Bessemer, and it's going to be everything as safe as possible, but still you're going to have crowds of people in buildings, which is not safe, but they're feel like they're forced to do this, and these will be um, helping advise students and helping them register. We cannot register students, okay? This new banner system does not allow it. So we won't be registering students, but we can be advising and helping and answering questions. I can't be there because of my health condition, okay? But other faculty members and staff and administrators will be at these places. On the Birmingham campus, it's in that new Academic Success Center. There's some big room somewhere there that they're going to have all set up for people to be advised and registered. They're going to have desks for general education, 2 of those. They're going to have desks for pre-nursing, desks for health profession, just desk everywhere, and perhaps multiple people at those desks to advise as many people as much as possible. They'll be starting that Monday morning at 9 o'clock in the morning and going through 7 o'clock in the evening, Monday through Thursday of next week. So if you know of people who are returning to campus in the in the spring, when I say returning students, whether they come to campus or not, please let them know they're having this big push. Now, my advice, and this is just my opinion, everyone should be doing virtual advising and then registering. I think it's not a good idea to meet as big groups like this, and it's not going to be big groups. It's probably going to be people filtering in, but still you're going to have so many people on campus. It's just not safe, okay? But they're going to be doing it. So let anyone you know that is a returning student for spring term, let them know if they haven't already registered. Try to register this week. Get your advising done today or tomorrow. And then get registered this week or this weekend, and then you don't have to go to campus. But if you're not completely registered and have any questions or issue, next week is going to be the biggest time to get the most questions answered possible. So please do that. So on the Birmingham campus, that's the new Student Success Center where that old Winona Elementary School used to be, that new building right there on Wilson Road. On the Bessemer campus, it's the Ethel Hall Auditorium, and that's not the Ethel Hall Nursing Building on the Birmingham East Campus, not that one. In Bessemer, on the Bessemer Ethel Hall building there, the auditorium there. They'll have everything spread out, and they'll have plenty of room for social distancing, plexiglass between advisors and advisees. Everybody will be in masks. It's going to be as safe as possible, but it's just not this. Be far safer to do it virtually, okay? If everyone were to get the virtual advising done today or tomorrow, get registered, and you don't have to go to campus, okay? So that's the announcement number 1. Announcement number 2, and since all 3 of you are in 3 classes of buying, Cal 3, linear algebra, and differential equations, you'll see this 3 different times. I posted it on Blackboard announcements in all 3 classes. Mr. Matthew West, I don't know if any of you know him, he's a sociology and history instructor at Lawson. He's mostly Bessemer campus, but he also teaches on Birmingham campus. He's working on his doctorate, and he's taking a statistics class, and part of that class is to design, develop, collect data from a survey, and then analyze the data. And his survey that he's chosen to work on, the project he's working on, is student opinions about face-to-face classes versus virtual classes versus online classes, especially in the light of the pandemic, and also has that pandemic influenced your education, in your opinion? And there's probably some other background information stuff. He said the survey takes only about 5 minutes or so, so I posted it out there. There's a link. Go to the link and do the survey. That's all you have to do. It's going to be totally anonymous. You will not be identified by name in any way, shape, or form. It just gives him data so he can do his statistics class that he's doing for his doctoral program at Alabama. So please help him out with that and do that survey as much as you can. Maybe some things about what's happening in the spring, just either skip those questions or say what you would answer if you were going to be in the spring or whatever. You can figure that part out. But some of the questions I know he would want the information for. Okay, so those are my two announcements. Just wanted to get those done. And when James comes in, hopefully he will come in, I'll go over them again with him. But if not, hopefully he'll hear it on YouTube videos. Okay. Now, Jesus, we're in chapter 4, vector spaces, 4.1 vectors in Rn, which we've been talking about. What you see on your screen here are the two basic operations in any vector space, including Rn, and these would be vector addition and scalar multiplication. Okay. And I was just leading up to, excuse me, anemia is still hitting me hard, so hold on just a minute. A little bit of caffeine and sugar maybe will help me keep rolling here. All right. Based on this, just like we did in 2-space and 3-space and everywhere else, we define a negative of a vector in Rn. Now, remember, either of these, u up here or v up here, vectors in Rn, they have n components. Well, what is the negative of u? Let's just say that would be the vector represented by negative u1, comma, negative u2, comma, negative u3, comma, dot, 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 comma, comma, negative u sub n. You just negate every one of those components. Well, why did I say that follows from here? That's just using the scalar multiple of -1. The c here is a -1, and that's what produces the negative of u. Now, you might say, well, here's the only vector addition. What is vector subtraction? Can you do that? Of course you can. U minus v would then be, just as defined before, vector u in Rn plus the negative of vector v in Rn. And then that would just be u sub 1 minus v sub 1, comma u sub 2 minus v sub 2, comma u sub 3 minus v sub 3, comma dot, 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 all the way up to u sub n minus v sub n. That would be your vector there. The difference of two vectors, just like you would expect. Now, here's the other thing, and this is the weird one. You've got to always have a zero vector in any vector space, even in Rn, and the zero vector in Rn was represented by the vector 0. That's the only time that it's not a letter, it's a number. The zero vector would be, open parentheses, 0, comma 0, comma 0, comma dot, 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 comma, all the way up to 0, the nth 0. There are n components, and they're all 0. Okay? That is your zero vector. You've got to have one. As useless as it seems like it is, you've got to always have a zero vector. All right, any questions? Let's move, all right, to erase. Okay, now here's example 4, bottom of page 155. And this one you can also go to larsonlinearalgebra.com and see an interactive version of this type of example. So here is a vector u. Let vector u, and the pen is not cooperating well, equal, and now we're going to be in 3 space. Okay, that's -1, comma 1, x, y, z, x1, y1, z1, or x1, x2, x3, whatever you want to call it. And v is also in 3 space, and its components are 2, -1, 5. Okay, both of these are elements in R3. Okay, it says perform the operations. Let's perform u plus v. Pretty easy going here, isn't it? U plus v would be u1 plus v1. -1 plus 2 would be 1, comma. 0 plus -1 would be -1, comma. 1 plus 5 would be 6. There is vector addition in R3. 2u, that would be 2 times the vector -1, 0, 1, which would be -2, comma 0, comma 2. There is vector multiplication. And then they have v minus 2u. Now you can write them out if you want to. I guess I should. That would be 2, -1, 5, minus 2 times, well, they've already, well, I'll write it out. -1, 0, 1. Okay? And this would be 2 minus, now I'm actually going to look up here and do this one because there's 2u right up there. Okay? 2 minus 2u. Well, I'm sorry. The 2 from here minus 2 from there. Minus a minus 2. Okay? That would be 4. Okay? -1 minus 0 would be, comma, -1. 5 minus 2 is 3. Okay. So there would be v. Or you could have done it this way. 2 plus 2, minus 2 times minus 1 is plus 2. That's your 4. Minus 1 plus 0 is, minus 0 is 0, is minus 1. And 5 minus 2 times 1 is minus 2. That would give you 3. And there you got it. 4 minus 1, 3. Any questions on those? It's example 4, page 155, right at the bottom of the page. Now they have a little technology blurb there on the side. You can certainly look at that and see if you want to use that. It's supposedly using one of the operators that this text uses is CengageBrain.com. I assume it works pretty well. I've never used it. I find Cengage products to be a little on the awkward side, and these are such easy things to do. I don't see any reason to go to the thing, but if you're interested in that, y'all are probably a lot more tech savvy than I am. Use it. Go for it. Okay? Now, flipping over to page 156. First thing I see on 156 is a picture of William Rowan Hamilton. Now he was, I think, considered to be, they say here, Ireland's most famous mathematician ever. And Ireland put out quite a few pretty good mathematicians and scientists and physicists and stuff, but William Rowan Hamilton really hit a lot of issues. Okay, you can read this if you want. This cannot be a source for your paper, but it can be the idea for a paper. You can write on Mr. Hamilton, but this can't be your source. It can be your source for your idea, but not the source for the paper. You'll need to find your sources elsewhere. Okay? Now, if I'm not mistaken, what he did in vector stuff, okay, that's a weird way to express it, was used in many years later and expanded, and he did a lot of stuff that we would never touch in a beginning course like this. I'm pretty sure he's the same Hamilton that in quantum mechanics that came about close to half a century after his death, they were using things from, oh, and here's James. Let me get James in here. So we have perfect attendance today. Way to go. Glad it's happening. Okay. That's perfect attendance for the week and for the last week and a half. So way to go, team. So James, here's what we were doing. We're in chapter 4, vector spaces, in section 4.1, vectors in Rn, and we're on page 156. And I was just talking about William Rowan Hamilton, who did much of the early work in vectors and vector spaces, but boy, what he did went way beyond a first course in in linear algebra. I mean, way beyond it. And I was just saying that in quantum mechanics, that wasn't even developed until close to half a century after his death, physicists and mathematicians and scientists were using things that he represented in his life and in his work. I'm pretty sure it's the same thing. It's called the Hamiltonian. Okay, it's a notation that they use in quantum mechanics, and of course quantum mechanics wasn't even dreamed of back at the time that he did his early work in math. Now, I may be wrong on that. Maybe it's a different Hamilton, but I believe it's him because it's close enough to the same subject matter. I think they named it after him. Now, James, also, I've been telling the others this, 2 announcements. The first one really has no direct implication for you, but it's indirect. And that is enrollment for spring term is way low, way low. And so the administration is almost in a panic mode, and they're having all instructors who can, I cannot, but all instructors who can, to return to campus next week, all 4 days next week, Monday through Thursday, from 9 in the morning until 7 in the evening. Not everybody will be there the whole time, but somebody will be there the whole time. And they're having a special advising registration deal going on next week, Monday through Thursday, 9 in the morning till 7 in the evening. Now, my advice would be, I know y'all aren't returning to campus, you're not registering, but I know you know people who will be and should be coming back to campus in the spring. I don't mean literally coming back to campus, but taking classes in the spring. Okay, my advice to them, and you please pass it on, is try to, if at all possible, get advising done today and tomorrow so that next week you don't need to go to campus and be exposed to all those people. Now, if you need to, if that would be what you prefer, please go. Everybody will be masked. Everybody will be social distance. The tables are going to be set up in big rooms. There will be plexiglass between you and the instructors. It'll be as safe as can be possible on campus, okay? But if you can do it remotely, if you can do it virtually, way safer that way. So encourage your friends, classmates, others you know, get registered before next week if possible. Get advised today or tomorrow, get registered next week or over the weekend, anytime, but try to get it. Or go to campus next week and get it done then. Okay. Now, the second announcement is not as crucial for the college, but it is pretty important. Mr. Matthew West, who is a sociology and history instructor here at the college, is working on his doctorate at University of Alabama, and he is doing a statistics class now. And in the statistics class, they needed to come up with a project that they developed, implemented, analyzed, and that kind of stuff. I put the links in all three classes you're in with me, Cal 3, linear algebra, and differential equations. You'll find the same thing there. You only need to do it once, but please do the survey for Mr. West so that he can collect his data and do his analysis and hopefully get a good grade because of it. Your name, nothing will be used. It's asking mostly about attitudes or things about face-to-face classes, virtual classes, online classes, and also whether you count that COVID has adversely affected your educational process. Those are the kind of things it's going to be dealing with. He says it'll be 5 minutes or around 5 minutes to do the survey. Please do the survey. Help him out in his pursuit of his doctorate. So those are the two big announcements there. Now, back to linear algebra again. Chapter 4, vector spaces, 4.1, vectors in Rn. Here is theorem 4.2. Now, you saw this almost the exactly same thing at the very beginning of the 4.1. In fact, is theorem 4.1. Okay? The only difference is 4.1 was dealing with R2, vectors in the plane. This is dealing with Rn. And you'll see these are identical, except for the fact one's two-dimensional, one's n-dimensional. Okay? And of course with, no, even then. Okay. All right. So I'm going to go over these again because guess what? You're going to see them again and again and again and again. So might as well get used to them. Here's what they are. These are the properties of vector addition and scalar multiplication. The two basic operations that define what we'll later be calling vector spaces. So you're going to see it all chapter, and this is probably the last chapter we'll get to, so the rest of the time in the course you'll see these. So here's the deal. Vector u, vector v, and vector w are all vectors in Rn, in space. Okay? And C and D are scalars. Any real numbers in the world. Positive, negative, fraction, decimal, rational, irrational, it doesn't matter. We keep them in the real numbers, okay? No complex numbers. A lot of times we'll sort of avoid zero, but they could be zero as well. There's nothing precluding zero. It just doesn't make sense sometimes. Here are those same 10 operations we dealt with. Okay, first, vector u plus vector v is closed, is going to be a vector in Rn. Now what does that mean? If you take a vector in Rn, add it to another vector in Rn, you can't be in some other space. You will be in Rn. Okay? Now that's called closure under vector addition. You may wonder why I'm writing this. It's because writing tends to go faster than printing. Printing, this board just does not do well. Here's a second, another addition issue. If you have vector u plus vector v, now both of these are in Rn, that's going to be the same as vector v plus vector u, also in Rn. Okay, and that is commutative property of vector addition. Okay, I know that's hard to read my sloppy writing. Okay, they don't always say vector addition. Since we're talking about vectors, I think it's good to say it. You can have scalar addition. These are the same properties that you would see. These are specifically vectors. Here's a third one. If you're adding vector u to vector v and then add it to vector w, you get the same result as if you had added vector u to the sum of vector v plus vector w. Okay, that's the associative property of vector addition, if I could write. Okay, these pens are just awful to try to write with. Okay, that's the third one. The fourth one, and this is exactly what theorem 4.21 was for two space. Okay, if you take vector u in n space and add to it the zero vector in n space, meaning zero components of zero, this is n components of zero added to n components of the vector u, you're going to always reproduce vector u. Okay, that's the additive identity property. Okay, ugly writing. Okay, number 5, the last of the addition ones, and this is if you have vector u and add it to the opposite of vector u, you're going to get the zero vector. Okay, that's the additive inverse element, additive inverse property they call it. I'll just put, that's supposed to be a tick mark there. Okay, now let's get into the scalar multiple part. Okay, 5 of these are addition. Here's the other. Starting off just about like we did here. If you take any one of those scalars, multiply it by any one of those vectors, you will still be in Rn. That means that multiplying by a scalar keeps you in the same space. Okay, and this is closure in vector in scalar multiplication. Okay, number 7. I'm not writing very efficiently here. I'm so sorry. I've got to get something else. My energy level is going to 0. Sorry about that. All right, number 7. What if you had some scalar c and multiply it by the sum of two vectors? Well, hopefully just as you would imagine, the sum of two vectors is a vector. A scalar times a vector is a vector, so you should get a vector out of it, and the vector you get out of it would be c times vector u plus c times vector v, which would be the sum of two vectors, which would be a vector. And this is the A distributive property of scalar multiplication over vector addition. Okay, that's a lot of abbreviation there, and the pen just isn't writing well, and I'm not writing well. Number 8. Slightly different type of distributive property, and that would be if you have two scalars, c plus d, distributive over a vector u, that would be cu plus du. Okay, it's also a distributive property of, this is so aggravating, okay, basically scalar multiplication over scalar addition. Okay, scalar, where in the world did the pen go? It was just here. Okay, scalar multiplication over scalar addition. Okay, because you're distributing the c and the d across the parentheses. Okay, number 9. This aggravating thing. Now, this is the closest you can get to an associative property. If you have c times, that's the scalar c times scalar d times vector u, that's the same as scalar c times scalar d times vector u. Okay, and that would be associative property of two scalars multiplied by a vector. Associative property of two scalars with one vector. Okay, gonna have to sort of leave that one hanging there. Okay, they just call it associative property, but you know, they say associative property of multiplication. If I were to read that and said properties of vector addition and scalar multiplication, I would assume that I know it would only have to apply to one vector with multiple scalars, two scalars. Okay, but they are not very clear with that, so I write it out. And then the last one is a pretty simple and straightforward. The number 1, scalar 1, times any vector, is it u? I think it is. Doesn't matter which one it is. It's always equal to u. If that scalar is 1 multiplied by u, you always get u out of it. Well, that is your multiplicative identity element. 1 is the number 1. Multiplicative identity element. Okay, this writing is so terrible. Okay, they call it multiplicative identity property. Now, using those 10 properties from this theorem, you can perform algebraic manipulations with vectors in Rn in much the same way you do with real numbers, as demonstrated in the next examples. So let's move to that. Okay. Any questions on this before we move? Okay. So here is example 5. Let U equal, it's a vector in 4 space, 2, -1, 5, 0. Now I can't pretend or imagine hardly what they're talking about here. I can't picture 4 space, but it's a perfectly good, valid mathematical concept. Okay. Vector V also in 4 space. How you know it has 4 components. So vector V would be 4, 3, 1, -1. 4, 3, 1, -1. And vector W here also in 4 space, -6. And it threw away my negative sign. This thing just aggravates me no end. 0, 3. These are all 3 vectors in 4 space. Okay. Elements of R sub 4, super 4. Okay. It says find X using each equation. So that's what we're looking for, X. And here's the first one, which is pretty straightforward. X is equal to, and this is a vector X here, by the way, is equal to 2U, 2 times vector U minus vector V plus 3W. Okay. Goodness, I'm losing it fast here, folks. I'm so sorry. Let me drink some water. Maybe that'll boost me a little bit. I feel like every day I'm getting a little stronger and less anemic, but it sure is moving slowly. I need to be probably eating more raisins. My wife said she found out or read somewhere they were good for restoring red blood cells, so I'm going to try to do that this afternoon. All right, so what do we have here? This should equal 2 times vector U, which is 2, -1, 5, 0, minus vector V, which will be 4, 3, 1, -1, plus 3 times W, which is -6, 2, 0, 3. close two parentheses there. Okay, now let's hit it as we go. If I could get my pen to show up here. There it is. Goodness, it's just all over the place. Okay, here we go. This would be, I don't touch the board and it writes. I'm trying to find it and it doesn't show up anywhere. Let me just keep this from being any messier than it has to be. Okay, 2 times 2 would be 4, comma, negative 2, comma, 10, comma, 0. Minus. Now let's do what's in the parentheses first. 4 plus 3 times negative 6 would be minus 18. 4 minus 18 is minus 14, comma. 3 plus 3 times 2 is 6. 3 plus 6 would be 9, comma. 1 plus 3 times 0, if I can read my writing there, that would just be 1. Okay. And minus 1 plus 3 times 3, that would be 9. Minus 1 plus 9 would be 8. Okay. Now we really don't need the outside set of parentheses now, but I had it there so I'd close it out. So this would be 4 minus a minus 14, that would be 4 plus 14 would be 18, comma. Negative 2 minus 9 would be a negative 11, comma. 10 minus 1 is 8, comma. 0 minus 8 is negative 7. Negative 8. I don't know where that came from. Negative 8. Okay. I don't know where any of those came from. 10 minus 1 is a 9. Like I say, my brain is giving up on me. That's a 9 and that's a negative 8. Let me make sure I'm right on that. 10 minus 1 is 9, and 0 minus a negative 8, minus an 8 would be a negative 8. Alright, I hope that's it. I don't want to go back and redo this one. Okay. 18, negative 11, 9, negative 8. Got it. Okay, that was the A part. The B part. Okay. 3 times x plus w, vector x plus vector w, is equal to 2u, 2 times vector u, minus vector v plus x. Now, remember what we're looking for. We're looking for x, okay? So before you start plugging in numbers here, it's probably a pretty good idea to solve for x. So this will be 3 times x plus 3 times w, that's just a distributive, okay, is equal to 2u, that's just a number, minus v, which is just, a vector number, plus x. Okay, let's subtract the x from both sides. This pen is not being very helpful. Okay, subtract an x from both sides, vector x from both sides, just like you would do it if it was scalar numbers. Okay, and let's go on and subtract a 3w from both sides because we want to isolate x on one side. Yeah, so it will be a minus 3w over here. Okay, now obviously these two add to 0 and these two add to 0. Oh man, I am so tired. So what we have here is 2 times x. If I could get my pen to move. There we go. This would be 2 times x is equal to 2 times u minus v minus 3w. Okay. Now, I would say let's go on and divide everything by 2. Okay, and that would leave us x, vector x, which we don't know, is equal to, here of course these 2's went out. Yuck! Why in the world did that do that? Okay. I'm sorry folks, I've got to have something else to drink. Okay. Those 2's went out. The pen just is all over the place. Those 2's went out. These 2's went out. So that leaves you just a u minus, and I'm going to write it this way, 1/2 v minus 3/2 v. No, w. Okay, sorry. The old gray cells aren't working well. Okay, so this is going to be vector u, which is 2 minus 1, 5, 0, minus 1/2 of vector v, which is 4, 3, 1, negative 1, minus 3/2 vector w, which I'm not sure I'm going to be able to squeeze in here, but I'm going to try, negative 6, 2, 0, 3. Whew. Okay. So let's see what we got here. I'm going to try to combine as much of this as I can, as easily as I can. This will be a 2 minus 2, that's 1/2 times 4, minus, and that's going to become a plus. Okay, 2 will go into 6 3 times. 3 times 3 is 9. So there's our first component. Second component is going to be a minus 1. And here we have a minus 3 times, a minus 1/2 times minus 3. That's going to be a minus 3/2. And the third one is going to be a minus 3. Okay, that's the second component. Third component is going to be a 5. And this is going to be minus 1/2 and 0. Okay, so that saves some writing a little bit there. This is going to be a 0 plus 1/2, and this will be a minus 9/2. I don't know if that was someone trying to contact me or what, but I just heard a blip. Okay, so let's see what we've got here. 2 minus 2 adds a 0, so this is going to be 9, comma. Here we have a minus 4 minus 1.5, that would be minus 5.5, which would be minus 11/2. I hope. I'll come back and check that in a minute. And this is a 5 minus 1/2 would be 4.5, which would be 9/2. And then the last one is going to be 1/2 minus 9/2 is minus 8/2, which is a minus 4. Let's see how we did on that. 9 minus 11/2, 9/2, negative 4. Amazingly, we got it. All right, so that was example 5. Can we do example or theorem 4.3 in 3 minutes? Let's try just to see if we can. Any questions on this example before we move on? Follow all the steps? I hope so. I wish we were in class. I hate talking to ether space. It just drives me nuts. Okay? I would hate even worse doing an online class which there's nobody even there to talk with. Excuse me. The zero vector in Rn is also called the additive identity element in Rn. We hit that in those, remember back on those numbered 10 numbered thing, number 4 was u plus 0 is u. Okay, that's where that comes from. Similarly, the vector minus v is the additive inverse of v. Well, that was theorem 4.2 number 5. Okay, the next theorem summarizes several important properties of the additive inverse and additive identity and additive inverse of in Rn. Okay, so this is just an expansion on what we just talked about. So vector v is going to be in Rn, element in Rn, meaning it has n components, and c is a scalar, any real number. Okay, this pen is not being very helpful in writing. Then these properties are true. Only 6 of these. First, the additive identity is unique. Okay, now that almost seems to me to be self-evident. Okay, here's how you express that. If v plus u is equal to v, then that implies it has to be true that then u is the zero vector. The only way it can be. Okay, that's the only vector you can add to some other vector and not change the value of that vector. Every element has to be 0. So that would be that one. Okay, number 2. The additive inverse of v is unique. Additive inverse is unique. This is just so aggravating, that pen. Okay, what that means is if v plus u, this is so aggravating, if v plus u is equal to 0 vector, means they're additive inverses of each other, that implies it has to be that u is equal to the opposite of v. It has to be. No way around it. Okay, the next three are a little shorter. Okay, the third one is this one. That 0 times V, now that's the number 0 times the vector V, is always going to produce the 0 vector, because this is a scalar. Remember, C is a scalar times a vector gives you a vector, but that changes every component in V to 0. Okay, now very similar to that one, number 4 is that C, any scalar C, multiplies by the 0 vector. That's a vector. This is going to be the 0 vector because there's no way around it. That's basically the multiplicative identity element, okay, which we did before under, maybe we didn't say it. We did. No, okay, I'm sorry. Is the 0 product principle. I'm sorry, that's the one I was thinking of. Number 5. For some reason the pen has moved over there. This sort of combines the last two. If CV is equal to 0, okay, that implies that either C is equal to the number 0 or V is equal to the 0 vector. No way around it. It's got to be one or the other. And then the next one is kind of a byproduct of others, and that's the opposite of V is going to equal to V. Okay? Now, each one of these can be proven. The proof basically is to take it back to your components. That's the best way to do proofs, anything in linear algebra or in vector spaces, is to take it back to the components. That's a bit of a broad statement, but it usually works. There's a linear algebra at the bottom of page 157. If any of you have had your physics, you've probably run into that problem there too. Certainly worth a look. We almost finished. Whoa, I went over, didn't I? Almost finished this section. We will finish it next time. Let me get my pencil. We'll begin next time on page 158, and we will go from there. Homework exercises here would include: number 1 should be at calcchat.com. 3 or 5 should be at calcchat. 7 or 9 should be at calcchat. 11 through 15 should be at calcchat. 17 should be at calcchat. 19 through 23 should be at calcchat. 25 or 27 should be at calcchat. 29 or 31 should be at calcchat. 33 should be at calcchat. 35 or 37 should be at calcchat. 39 should be at calcchat. And hang off there, we'll be doing linear combinations once we finish page 158. So we'll pick up and go from there. Any questions on what we've done so far in 4.1? Okay. Now, I can't remember if I got the third test out there for you. If I didn't, hopefully I can get it there either sometime today or sometime tomorrow. Okay. Sorry if I didn't, but Thursday's classes went until close to 7:45 in the evening, and I was beat. Tuesday's classes, I was beat by the end of that, and basically I just had very low energy most of yesterday as well. So hopefully I'm getting a little stronger every day, but man, I'm beginning to look forward to first Thanksgiving week, but also finishing classes and retirement. I mean, I am between my treatments and that kind of stuff. It's just wearing me out like crazy. So take care, people. Be safe. Have a good weekend. but keep safe. The counts are climbing like crazy. Don't let down your guard. Keep your mask, keep your social distancing. It's worth it. You don't want to catch this disease. I promise you. Thanks much. Any last questions? Parting shots? I'm going to stop sharing now. Anything else before we go? Okay. Have a good weekend, which means have a safe weekend. Okay? Bye-bye.